All right, so before getting started, I just want you to be aware that the slides are already available online. You can go to that URL or scan the QR code. I also dropped the link in the Discord channel if you're there. The reason why I like to share them is because I'm going to be showing you a bunch of code examples, some links, but we only have limited time, so I will probably have to rush through some of this material. Okay, so let's start by telling you what is Rust. And you know that the most loved language and blah, blah, blah. So yeah, I'm not going to bother you with all of that, but I'm just going to tell you why I actually like Rust, especially in the context of AWS Lambda. So there are some features of Rust that are really interesting. The first one is this concept of zero-cost abstraction. So if you come from the C++ world, you're probably familiar with that idea. Otherwise, the concept is that basically, as a compiled languages, you are taking your source code and you are producing a binary. And the idea is that only the features of the language that you are actually using should be included in the final binary. So that basically means that your code, when it's compiled and it's running, should be as efficient as possible because it doesn't carry the baggage of, for instance, a runtime where maybe there are 1 million features that you are not even using. And that's really important in the context of Lambda because it's one of those things that will make sure that your code is going to run as fast as possible. Also, there is a very good, strongly typed type system that is probably inspired by other languages like Haskell. And we can see that there are other features. We already mentioned C++, but there are other features like async await, probably coming from .NET and JavaScript, closures coming from JavaScript and Ruby. So other things coming from OCaml. So if you know any of these languages, there are lots of things that will feel familiar to you when starting to learn Rust. There is a package manager, and it comes built in with Rust. So when you install Rust, you also get the package manager. So if you use JavaScript, for instance, that will be the equivalent of an NPM. And because of that, there is a great ecosystem of libraries that is already out there and available, probably not comparable yet to the size of NPM, but I've been using Rust for the last 4 years, and every time that I needed a library, I was able to find it, and generally it's very good quality. And then there are lots of features in the language that I really like. I'm going to be showing you some examples in a minute, but I can mention pattern matching. There is no null type, and the lack of no-null type is fulfilled by a type called option. And then there are no exceptions because there is a type called result to trap errors. Now, I'm not the only one who likes Rust. I don't know if you recognize this blog. If not, you can click the link and check it out later. But yeah, I just want to show you one quick example just to try to explain with a real practical use case why some of the features of the language are very powerful. Now, this is a very simple line of code. We are basically just trying to read an environment variable. And this environment variable is called AWS region. In many programming languages, when you assign something like this, on the other side, what you get is a string. And it's on you to check if the environment variable was actually set or not, and then decide what to do with that. In Rust, actually, you don't get a string straight away, but you get a type called result. And this type tries to make sure that you are taking care of the two possible outcomes that you can have. And the first outcome is what we can call the happy path, which is basically the string was set, so we can get a string out of it. So the environment variable was set, so we can get that string. Or if the environment variable was not set, this is the sad part, we need to figure out what do we want to do. We don't have that value, so what are our options? And we need to think about that. There is no obvious solution. So the result type gives us a few different ways to handle the different cases. And the most explicit one is this match statement. So this is pattern matching, which allows us to make sure that we are actually exploring all the possible paths. And in this case, we only have two paths. So either is OK, which means the value was set, and we can access the value and calling it region. So we are effectively shadowing the original variable. At that point, region is going to be a string, and we can just print it in this case. Or if the value was not set, this is going to be an error, and we can decide what to do with that error. For instance, just printing, well, the environment variable was not set. Now, of course, this is a dummy representation. Probably you want to have slightly more sophisticated logic in the two branches, but it's forcing us to write code that handles both cases. Another option is maybe if we don't have this environment variable set, we cannot proceed. So what we can do is assume that the environment variable was set and read the value as a string. And if it was not set, this is just going to panic our executable, and it's just going to crash the program. And we can do that with a function called expect, which is kind of a shortcut, that what it's going to do is basically assume the happy path is going to happen. If it doesn't happen, it's going to crash the program. But that allows us to access the string straight away. So it's a little bit of a shortcut that is maybe acceptable only when you cannot continue if the value was not set. And also when it's acceptable to crash the program if the value is not there. Another option is maybe when you can just use a default when the value is not there, and you can use this other helper function that will allow you to set a default when the environment variable was not set. Now, the point that I want to make is that thanks to this type, the result type, but there is another type that is called option that helps you to deal with the absence of values. Rust makes it very difficult for you to ignore specific edge cases. So I find, at least myself, every time I'm writing a piece of code in Rust, that the language itself forces me to think about what happens if this case is happening. And by doing that, I think you're going to be writing code that is much more resilient. By default, you're going to be handling all the cases, and probably you're going to write less bugs in your code. So that's a great feature of the language. And it's really important also in the context of Lambda. But if we want to zoom in, what are other reasons why Rust and Lambda work so well together? So we already mentioned that Rust is very performant because of that zero-cost abstraction, but also because it's a compiled language. And also it's very memory efficient. And this is by design because, for instance, it doesn't have things like a garbage collector. And again, the zero-cost abstraction makes sure that the amount of memory that is used is really the minimum amount of memory needed for the kind of program you're writing. And if we think about Lambda, one of the main costs that we pay with Lambda is the invocation cost. And invocation cost is basically an amount of memory that we are allocating for our Lambda, which has a unit of cost associated to it, that we need to multiply for the number of milliseconds that our Lambda function instances are running. So the idea here is that if we can reduce the amount of memory we need, and if our code can run really, really fast, we are basically optimizing both the dimensions of pricing. So that makes it possible for writing Lambda functions that can be very, very cost effective. And another thing is cold starts. Because the runtime is, effectively there is no runtime, loading a Lambda, a Lambda that contains a piece of Rust code is generally very fast. So the bootstrap itself is very fast. The binary can also be very small if you're not using a lot of external libraries. So that means that your cold starts are generally really, really quick. And personally, I've seen cold starts in the order of 10 to 30 or 40 milliseconds. And if you compare that with other languages like JavaScript, Python, or even worse with Java, you see that it's like noticeable difference. You are going like at least 10% of the cold start that you have with other languages. So that can be really good if you're writing, for instance, APIs where you want the response to be really as quick as possible, even in the case of a cold start. Now, multi-thread safety is another great feature of Rust. To be honest, this is not the main one because generally you don't end up writing a lot of multi-threaded code in Lambda. But if you ever need to do that, the language itself is going to help you to make sure that you don't do the common mistakes that you can do when you write multi-threaded code. And then we already saw some examples of the no null types, and there are great error primitives with general results in writing code that is a little bit more resilient. So if all of that is exciting, hopefully today we're going to see how to get started with writing Lambda functions using the Rust programming language. But before we move on, let me tell you very quickly about myself. Hello, everyone. I'm Luciano. Thank you for being here. I have some interesting badges there, and I work as a senior architect for a company called Fortiera. More on that in a second. But before that, you might have seen my name if you are in the Node.js ecosystem, because I'm one of the authors of this book called Node.js Design Patterns. If you read the book, please let me know what you think, because I'm always looking for feedback. Maybe we'll write an edition. So if you have any suggestion, I'd love to hear it. And feel free to connect with me. You'll find me online on Twitter, LinkedIn, all the other major social networks. So feel free to connect. I'm happy to chat anytime, even after the conference. Okay, a little bit about Fortiera. We are a consulting company. We are AWS partner, really focused on AWS. We do lots of serverless projects. And we have been helping our customers to be successful in the cloud, doing a bunch of different activities from building entire application from scratch to optimizing and refactoring and modernizing existing applications. We have been also writing some Lambda function in Rust. So if that's a use case you want to hear about, we can talk after this presentation. And we also do a lot of content creation. I'm actually very proud of this. We write lots of articles. We also have a podcast called AWS Bytes. And so it happens that we have an entire episode dedicated to how Lambda runtimes actually work under the hood, which is something I'm going to mention briefly. But if you want to kind of deep dive, maybe this episode can be interesting for you. Okay, let's get started. Where do we start? We can start by trying to create a new Lambda function in the AWS web console. So generally speaking, what do? You just go on the Lambda service, you click on create a new Lambda, and then at that point, you have a screen that looks like this. You have to give a name to your Lambda function, and then you have to pick a specific runtime. By default, it's giving you Node.js. But of course, we want to use Rust, right? So we click in this drop down, and we start to see all the available options, and we quickly realize that Rust is not even there. So what I've been talking about, right? But then if we squint, what we see is that if you look at Amazon Linux 2023, it's basically saying, well, this is what you need to use if you want to use Go, Rust, C++, or even do something custom. So easy peasy, we just need to create a custom runtime. And you might be wondering, what is even that, right? And we need to zoom in a little bit on how Lambda works. And actually, we are used to think about Lambda just as a handler function, but in reality, there are two components to it. One component is the handler function, so the actual business logic that we need to write for our Lambda to make sense. But there is another very important component, which is the runtime. And we are not always aware of that because when you use Python, Node.js, or Java, that's entirely managed by AWS, so it's kind of almost hidden. You don't have to even see it. You just write your handler code, and everything else happens magically. But that component, nonetheless, is there for every single Lambda function. Now, when you write a custom runtime, it is a little bit more obvious. You need to understand how it works, why it's there, and what is it doing. So let's try to understand all of that very quickly. So the idea is that when a Lambda function starts, you can imagine that it's like a virtual machine that pops up somewhere and doesn't really know what to do. It's just there, and it's like, what do I have to do? So somebody needs to tell that virtual machine what it needs to do. And the mechanism is that this component called runtime goes on a loop, polling the control plane in AWS and basically asking, is there an event for me? Is there something that I can do? And at some point, there is going to be an event, which is effectively a JSON blob that represents something important that is effectively the input data that is going to go into our Lambda execution. And the runtime is responsible for taking that information, converting into something that the specific handler can process, and just waiting for a response. So the handler at that point is going to run, and it's going to produce either a response or an error that is sent back to the runtime, and then the runtime needs to send it back to the control plane. Now, the reason why it needs to go back to the control plane is because imagine you are building like an HTTP Lambda. Something needs to know what is the response to send the TCP connection that the client has established with the initial request. So as a Lambda, we only think about the handler. We receive an input, produce an output. But of course, we need to have this kind of glue code that talks with the control plane and connects everything else. So if you don't believe me, there is an easy way to see that all of this is happening. If we actually click create on that Lambda function screen we were looking at before, surprisingly, it's going to give you something written in Bash. So I don't know who was crazy enough to write that in Bash, but it's actually written really, really well. It's really clear and understandable. If you go through it, there are even nice comments. And we can see very quickly that there are 4 distinct parts. The first part is basically this is loading another Bash file, and that Bash file will contain our business logic. So this is effectively a reference to the handler. Then the other part is that there is a while true. So this is the endless loop where we are effectively doing something continuously. And what we are doing for every iteration is polling a specific endpoint which exists in that environment variable. And if you actually look at it, it's a local IP address. So effectively, this is the socket to the control plane. And we call a specific endpoint, which is going to check, give me the next event. When we get a response there, the next event also has an ID. So at that point, what we can do is go to the next step and invoke the handler with the event payload. And when we receive a response, we have the ID from the previous request, we have the response from the handler, and we can send everything back to the control plane. So at that point, we are completing the request lifecycle, and the control plane is going to do the rest. Now, of course, we don't want to rewrite all of that in Rust. Thankfully, AWS has done that for us. There is a custom Rust runtime that is built and maintained by AWS. And thankfully, it's very easy to use. We can just include it as a library in our code, and it's going to do all this magic for us. But now at least you know what's going on behind the scenes. So the next step is installing Rust. There are many ways to do that, but the way that I prefer is using this tool called Rust App, which is a simple script that is going to allow you not to just install Rust, but also to install all sorts of different add-ons. Like, for instance, between architectures, you need certain add-ons, and this tool is going to help you to install everything you need. There is another amazing tool that is also written and managed by AWS called Cargo Lambda. This is an extension of the package manager, and what it does is basically it's going to give you all the tools to work with Lambda function when you're using Rust, and we will see some examples. And the first example is, where do I even start? How do I even scaffold a new project? And Cargo Lambda will give you a CLI utility called init that is going to guide you to creating your first Lambda. In this example here, we have seen that basically it's going to ask us, what kind of event are you interested into? And we are selecting S3. And when we confirm, we're going to get some code that looks more or less like this. And we can see that there are some interesting parts. The first one is that we are using this Lambda runtime, so the one I mentioned before. Cargo Lambda is going to install everything for you automatically. It's going to create all the code that you need. So effectively, it's already importing the library and configuring it correctly. And where is that library actually being used? It's then in this main function. So you can imagine that this is the init phase of your Lambda function. So this code only happens the first time that your Lambda is starting. And what we need to do here is setting up all the clients, loggers, and then at some point start this loop of polling for events. So here we are setting up the tracing is kind of a logger tracing utility that you have in Rust. And then this run function comes from the runtime and is basically doing that loop and calling the function handler every single time there is a new event. Now, this is the code that we actually need to worry about. This is where our business logic goes. This is the function handler. And here is actually very simple. What we are doing is we are just logging every single record in this S3 event. But of course, here you will probably do something more interesting, like, I don't know, maybe reading the content of every single S3 object, maybe fix an image, create a thumbnail, whatever is the business logic you want to implement. Okay, how do we test this? And if we use Cargo Lambda again, Cargo Lambda gives us two very useful features. One is called Cargo Lambda Watch, which is going to start a local simulator that watches your file. So every change you do is going to rebuild your Lambda function and make an endpoint available locally. Then with another command called Cargo Lambda Invoke, you can pass an arbitrary JSON or use some of the predefined examples to invoke your local Lambda and say, okay, I want to simulate an S3 event. Let me see if my code does what it's supposed to do. And you can see here that we are logging the objects in that particular S3 event. So this is really cool that you can immediately test your function locally, even before deploying it to AWS. Now, let's look at another problem. We saw an example with S3, but you might be wondering, okay, what if here I want something different? Maybe I'm not writing an S3 integration, maybe I'm writing something else. And also, what if we want to return a specific response? Because maybe it makes sense for us, for our Lambda function, to have a specific output type. And so what are the different options that we have to deal with different kinds of inputs and different kinds of outputs? And this is important because being a typed language is not like JavaScript or Python, where you can assume the input and the output can be anything. You need to think a little bit upfront about what are the types of the input and the output. And one thing that we can do is to use this library called AWS Lambda Events, again, maintained by AWS and by the same people that do the Lambda runtime and Cargo Lambda. This is effectively a collection of all the most common events that you have in AWS. So these are, I don't know if it's extensive, but I think it's pretty close to cover all the different integrations that you have in Lambda. And it's open source, so if you see something missing, you can do a PR. It's going to be very easy to integrate the missing events. But you can see that there is pretty much everything: RabbitMQ, Alexa, IoT, Firehose, ECR, Connect. So basically, you can write a Lambda function for any kind of integration. Just use this library, and you get all the types and type safety for the different kind of events and responses. And I want to show an example, and I think this is a pretty cool one that was already mentioned twice today by Simon and Raphael, which is when you are processing jobs from SQS using Lambda. Commonly, there is one problem, and the problem is that you receive events that contain batches of jobs. So your Lambda is going to have to loop through the batch, take every single job, do something, and of course, process the specific job. But what can happen is that if you have 20 jobs, maybe you are very unlucky, 19 succeeds and 1 fails. If your entire Lambda crashes, what AWS is going to assume is that that entire batch failed. So it's going to reschedule all the 19 jobs, all the 20 jobs, including the 19 that succeeded, which of course is not ideal because you might end up with double processing and you are wasting compute anyway. So actually, AWS has announced a feature that allows you to tell exactly which jobs failed and assume that all the others succeeded. So AWS can reschedule only the ones that failed. And in Rust, this is actually very convenient because when you use cargo lambda init and you select SQS, it gives you already something that looks like this, where if we look at the response type, the response type is called SQS batch response. And this is a type that already codifies the specific structure that AWS expects when you want to tell AWS this particular job or this set of jobs failed, please reschedule them for me. If you have to do this in Python and JavaScript, of course it's feasible, but you need to be very careful about constructing the object correctly. Otherwise, the response is not going to be used, and therefore you might end up with repeated jobs in the queue. So with Rust being a typed object, typed language that gives you all the structs out of the box, we can easily use the structure and say, push this job if it failed into the response. And then at the end, we return the response. Okay, another use case. What if I need to do something entirely custom? Maybe I'm not writing a specific integration between AWS services, or maybe I'm working in the context of a step function where I might need to have custom steps. And when you have custom steps, of course, you're going to have a custom type of input and a custom type of output. So how do we codify all of that? Actually, I'm going to go very quickly on this one because I did an entire series of live streams building this feature. So if you're curious, you can check it out on YouTube. There is a link there. But the idea here is that I'm managing automation for a newsletter. There are a bunch of steps. For instance, one of these steps is that I need to fetch a specific URL to get the number of the latest issue of that newsletter. And of course, there is a custom input and a custom output in that particular Lambda function, because this is an entirely custom type of flow. And there is a library in the Rust ecosystem called Serdi that allows you to do all sorts of serialization and deserialization, including the JSON-specific library. And what we can do, if we use this library, we can create our own custom structure and just write a little bit of annotation. For instance, we are saying this particular type called request can be deserialized from JSON, and we expect to find only one field, which is going to be URL, and it's going to be a string. Similarly, we can create a struct for the response, and at that point, we can just use in our Lambda function definition these two types as the event and the response type. And the amazing thing is that the Rust runtime understands this library, so it's going to do all the JSON serialization and deserialization for us. So we can just use plain types. We don't have to think about JSON anymore. Now, the other approach is, what if you need to use arbitrary events? So it can be any valid JSON. That can be very complicated to handle because, of course, you need to parse any kind of JSON in a strongly typed way. So it can be very ugly, but nonetheless, you can do it. So here you can see that it's very ugly because Rust forces you again to think about all the possible edge cases. Is the event an object? Do we have this key? Is the value associated to this key really a string? And if any of those assumptions are not correct, you need to figure out how do you want to handle those. The other thing is, okay, we didn't see HTTP lambdas, which is maybe the most common use case, especially if you want to use Rust, it's probably the most convenient. And the only thing I want to show you is that there is another layer of abstraction called Lambda HTTP, again, maintained by the same group of people and automatically installed when you use Cargo Lambda init and you select HTTP. And what it does, it gives you an even higher level abstraction for requests and responses, because it gives you practically a way to extract. This looks like almost like a web framework. It gives you ways to read the request, the headers, if there are query string parameters. And then when you want to build a response, you basically have a builder pattern that allows you to specify all the important fields, like the status code, response headers, the body, and so on. Now it's time to deploy this, and you can do basically Cargo Lambda deploy to deploy everything to AWS. But it's a little bit annoying because then you go to the Lambda console and you're going to see a few weird things. The first one is this blob there that doesn't mean anything. But actually, if we think about that, it makes sense because this is a compiled language. We only have a bootstrap file. I don't know if you can read it there. And this bootstrap file is a binary. So that it's kind of weird that you see it, but it makes sense. You are not expected to edit that code live on the web. You need to recompile it and redeploy. The other thing, which is a little bit more important and worrying, is that there is no trigger configured. So we deployed our Lambda, but nothing is going to run our Lambda unless we go here and trigger it manually, which is a little bit annoying. In reality, there is a little bit of a trick. If you are okay with using function URLs, you can enable that with Cargo Lambda using that flag. But the real way you should solve this problem is by using SUM or any other infrastructure as code tool. Now, I'm going to skip quickly on this part. Just be aware that you can use SUM with Cargo Lambda. And I have an example here on what the configuration looks like. You pretty much need to use this particular annotation to say, this is a Lambda, and it needs to be compiled with Cargo Lambda. And you can also do all the local testing. You can even use some local simulation. So it's going to start a local API gateway, and it's going to work with your Rust code. Now, closing notes, I think this is a great use case. You can use Rust today. I think the developer experience is actually really, really good, maybe even superior to other runtimes. My suggestion would be don't just go wild and think, okay, I'm going to rewrite everything in Rust. That probably doesn't make sense, and it's not going to go very far away with your PMs or managers. But if you have a specific Lambda that is running like millions of times a day and it's costing you a lot, or maybe you have a use case where your Lambda needs to be very fast, even when there is a cold start, you can maybe invest in rewriting that one Lambda. And the other suggestion is make sure you share everything you learn, because this is still a very new topic. And of course, in the community, we need to help each other with our learning, sharing our learnings and learning from each other. Now, I have some additional material. This is an entire example you can find on GitHub. This is an entire application also using EventBridge and other tools. There is an API gateway authorizer that we wrote, and there are benchmarks also compiling it with Python, so you can also check performance implications. And then I have one more thing for you, and then I promise you I'm going to stop. I'm writing a book together with James System about writing Lambda function in Rust. Price. The book is still in early review, so it is available. You can buy it today, and it's highly discounted, as you can see. There are right now only 4 chapters, but in these 4 chapters, you can already build a fully functional URL shortener using Rust and Lambda. And of course, we are going to be writing more chapters, and you're going to get all the updates. And for you in this conference, of course, the code is better. And that's everything I have for today. So thank you very much.